For all seafarers, weather has a large impact on their lives at sea and on the safe passage of their ship. A greater understanding of weather patterns can play a key role in ensuring safer voyages with fewer delays. In this two-part training package, we shall look in Part 1 at how weather systems are generated, and in Part 2 at how ships can best adapt to different weather conditions. The videos, which are accompanied by a booklet, are modular, and we recommend you watch one section at a time.
The Earth has a mean diameter of 11,040 kilometers, and the atmosphere which surrounds it stretches up a mere 480 kilometers, and it is only a tiny 16-kilometer lower layer of atmosphere, the troposphere, which has an effect on weather. If the Earth was the size of a grapefruit, this lower layer would be the thickness of just one sheet of tissue paper. All the weather is generated within this thin lower layer. During the 1990s, weather was the major cause of 30% of all ships considered a total loss by the insurance industry, by far the biggest single cause. During this decade, the number of serious incidents hardly altered, and the number of seafarers killed or missing due to weather-related incidents sometimes reached horrifying proportions. The number of incidents involving pollution was on a worryingly upward trend, and the number of ships lost also remained high. Of course, the problems of bad weather are familiar to all experienced mariners.
I just joined this ship in Trinidad. We were sailing northbound. We got word of this storm just north of Bermuda. Gearless bulk carrier. She only had about 6-7 feet freeboard, and we hit these waves that were absolutely enormous. I've never seen anything like it since. I reckon they were probably between 50 and 60 feet high. Certainly when you were in the trough, you could see these waves, and they were absolutely level with the bridge wing. Did result in quite a bit of damage to the hatches. One of our hatches, I remember, sank by about 6 inches. When we got to our destination, we found it had dropped 6 inches. The weather lasted for about 2-3 days, and we were actually driven in the reverse direction to which we were heading, almost 200 miles over a 24-hour period during that storm.
Avoiding bad weather at sea may help to save lives, but there are strong commercial benefits as well. With your ship on a tight schedule, it may seem strange that slowing down or taking a longer route will save money. But if there are storms ahead or other weather problems, that is indeed the case. To avoid the worst weather, navigating officers must understand what weather forecasts say and how they are produced. If the Earth's surface was uniform, the weather would be much more stable and predictable. It is because the areas covered by land and water heat up at different rates that weather patterns are established. The Earth is heated by the sun. The areas near the equator receive the greatest amount of energy because the sun's rays arrive almost perpendicular to the surface, and therefore have a shorter passage through the atmosphere. So the surface in these regions is heated the most. At the poles, the sun's rays arrive at a shallow angle. They need to pass through more atmosphere, and will therefore lose more of their energy through reflection and scattering effects. The remaining energy will also be spread over a greater surface area. Pressure is defined as force per unit area. So the air pressure at any point on the globe is proportional to the weight of air standing in a column above that point. Remembering that the atmosphere extends upwards about 480 kilometers, even a light gas, like air, will exert significant pressure on the surface. As one moves vertically upwards through the atmosphere, the air pressure steadily decreases. When part of the Earth's surface is heated, the air next to the surface becomes warmer. It expands on heating, and at an upper level it exerts a greater pressure than air in the surrounding areas at the same upper level. It naturally pushes out towards the areas of lower pressure, and a circulation is established. The falling, cooler air in adjoining areas exerts a comparatively higher pressure at the surface. So, areas at the surface with rising warm air are associated with low pressure, and those with descending cold air with higher pressure. On a planet with a completely uniform surface, the circulation of the atmosphere might be like this, with mainly low pressure near the equator and relatively high pressure at the poles. But the Earth has two particular complications. It rotates quite quickly, and there is an unequal distribution of oceans and land masses. The net effect is that there are three generalized circulations in the atmosphere. Having risen above the equator, warm air moves towards the poles, but having cooled somewhat, starts to descend at around 30 degrees latitude, giving rise to a belt of mainly high pressure. At the polar regions, cold, heavy air descends, and that circulation is completed by air rising at around 60 degrees latitude, from a region where low pressures predominate. In between these two circulations is a third circulation that flows in the opposite direction to the others. This represents an area of cyclonic disturbances. The general pattern is repeated in the southern hemisphere. The picture is further complicated by the uneven distribution of the major land masses. Particularly in the northern hemisphere, most of the land is found in the mid-latitudes. Land heats up more easily than water. Therefore, the generalized picture of surface air pressure is more like this. During the northern hemisphere's summer, there is low pressure at the equator and centered over the hot land masses, high pressure over the oceans and the colder land in the southern hemisphere. During the southern hemisphere's summer, there is low pressure at the equator and over the southern land masses, high pressure over the southern oceans and the northern land masses. It is these differences in surface pressure which give rise to one of the main characteristics of the weather: the wind. The prevailing winds move over the ocean from areas of high to areas of low pressure. They would generally follow a pattern like this, with winds converging on the low-pressure equatorial zone and on the mid-latitudes, with slight variations according to the season. But the Earth's rotation provides a second complication. This causes the winds to be deflected due to the so-called Coriolis effect. The best way to think of this is as follows. Imagine a body of air at a certain latitude. It has a certain angular momentum because the atmosphere of which it is part rotates with the surface of the Earth beneath. Now imagine this body of air is forced to move due north, away from the equator, because of a difference in surface pressure. As it moves north, its distance from the Earth's axis of rotation would decrease, as would its velocity around the axis. But any freely moving body always preserves its original momentum, so its angular velocity must increase compared to the Earth beneath. It therefore veers to the right. If the body of air was being forced to move south, the opposite occurs. At the start, both angular momentum and velocity around the axis are relatively low. As it moves south, its distance from the axis increases. But for its angular momentum to stay the same, it needs to slow down compared to the Earth's rotation. Again, it veers to the right. In the southern hemisphere, the same principle applies, but in reverse. Winds deflect to the left as they move towards the equator, and also to the left as they head for the pole. In the equatorial region, where change in latitude has virtually no effect on the distance from the axis of rotation, the Coriolis effect is negligible. There are, of course, many local variations, but the prevailing winds are, in the equatorial region, up to latitudes of about 30 degrees, the northeast and southeast trades, and in the mid-latitudes, mainly westerlies.
This tendency for winds to deflect increases with latitude, so some weather charts incorporate
The geostrophic wind scale,
which relates the spacing of the isobars and the latitude to the wind which is produced.
The geostrophic wind is the actual wind blowing at a height of about 600 meters. It starts blowing from high pressure straight towards low pressure, but is slowly bent round as a result of the Coriolis effect until it remains parallel to the isobars. At the surface, due to friction, the wind speed over the sea may be half to two-thirds of the geostrophic value. And because it is moving more slowly, the Coriolis effect is reduced. The wind's direction is about 10 to 15 degrees in towards the low pressure. The air in the atmosphere has low thermal conductivity and is not subject to constant mixing. So areas which are mainly cold tend to stay cold. Those which are warm stay warm, and those which are hot stay hot. So we talk about different air masses with quite abrupt boundaries between them. The air masses do move, but slowly. Their temperature and humidity depends very largely on where they originate. The principal air masses are Arctic maritime air, which originates over the sea areas near the poles. This will be very cold, and so the moisture content is also low. Arctic continental air, which originates over land masses at the poles. This is also cold and dry. Polar maritime air. Despite the name, this air originates over water in subpolar regions. As it moves to more temperate latitudes, it will gather moisture and become unstable, typified by cumulus clouds and squally showers. Polar continental air originates in the subpolar regions over land and is cold and dry. In winter, if it moves over relatively warm sea, it will start to resemble polar maritime air. Tropical maritime air originates over seas in the subtropics and is therefore warm and very moist. It tends to move towards the temperate latitudes, and passing over cooler water will often give rise to fog. In summer, if it passes over hot land, this air becomes unstable and often gives rise to showers and thunderstorms. Tropical continental air starts off hot and dry. It is likely to pick up some moisture when passing over seas, but not enough to trigger precipitation. Equatorial air is very warm, moist and unstable. Passage over hotter land areas will produce cumulus and cumulonimbus clouds to a high level and rainfall in large quantities. The movement of major air masses is usually slow and predictable. However, polar maritime air, after being warmed in its lower levels, sometimes turns back towards higher latitudes and assumes the characteristics of tropical maritime air. Then it is called either warm polar maritime air or returning polar maritime air. The boundaries between the air masses are the frontal zones: the Arctic front, between Arctic air and polar air; the polar front, between polar air and tropical air; and the narrow intertropical convergence zone, or ITCZ, where equatorial air lies between areas of tropical air. The mean position of the frontal zones moves up and down the globe, according to the season. When these large air masses, with quite different characteristics, meet, interesting phenomena can occur at their boundaries, and it is here that a lot of what we call weather arises. Where two air masses meet, the abrupt transition is known as a front. Where a warm air mass meets a cold one, it tends to ride up over it, being composed of less dense air. For example, the polar front, where cold polar air meets warm temperate air, will be wedge-shaped in cross-section like this, though in reality the slope of the boundary can be as shallow as 1 in 200. Being deflected by the Coriolis effect, the two air masses slide past each other in opposite directions. This situation would remain stable except for conditions at high altitude. If there are narrow and concentrated high-speed winds, the jet stream, in the same locality, they tend to suck air up from the lower level. Consequently, a low-pressure area starts to form at the surface, and winds flow in to restore the balance. The warm, moist air spirals up, giving rise to clouds and precipitation, and the latent heat released by this intensifies the whole process. The cyclonic rotation is anti-clockwise in the northern hemisphere, clockwise in the southern. The intrusion of warm air becomes more pronounced, with the heavier cold air pushing down the flank. A distinctive warm sector is formed. Localized pressure continues to fall, and the familiar depression is born. It is characterized by isobars forming closed loops and is moved along the line of the polar front by the jet stream winds at the upper level. Usually, a cold front moves round more quickly than the warm front, because it is the leading edge of cold, denser air, pushing up the warmer, lighter air. So a warm front advances at 30 to 50 kilometers per hour, say from 17 to 25 knots, while a cold front can move forward at 60 to 80 kilometers per hour, about 35 to 44 knots. In overtaking the warm front, it forms an occluded front, which means that the sector of warm air is no longer in contact with the surface. As we saw before, at the surface level the winds bend in at an angle towards the low pressure. The circulation of winds around a depression in the northern hemisphere is anti-clockwise, in the southern hemisphere it is clockwise. This fact is conveniently expressed in Bayes-Ballott's law, established in the mid-19th century. If a mariner stands facing the wind in the northern hemisphere, the pressure is lower on his right-hand side than on his left. In the southern hemisphere, if he stands facing the wind, the pressure is lower on his left-hand side than on his right. Not all depressions are associated with fronts. Thermal depressions occur where there is unequal heating of land and sea surfaces and little wind. For instance, an island or peninsula in the tropical summer will heat up relative to the surrounding waters. Air will expand vertically, giving rise to relatively high pressure at the upper level and sideways spreading. The air column over the peninsula is now less heavy, so there is low pressure at the surface. A circulation is established. As the air which flows inwards is moist, thunderstorms and squalls may be expected. The release of latent heat of condensation further stimulates the system. A polar or instability depression is a secondary depression which arises in the wake of a frontal depression. The cold polar airstream is being dragged over relatively warm ocean. Water vapour condenses, and again the latent heat of condensation causes air to rise and produces low pressure at the surface. Instability depressions are often less than 200 miles in diameter and may well arise in areas not well covered by observation. So they may not show up on weather forecasts, but they are important because a secondary depression can sometimes intensify and become much more vigorous than the primary depression it is replacing. The most important type of non-frontal depression is the tropical revolving storm. This represents some of the worst weather conditions a seafarer is ever likely to encounter, being smaller and usually much more intense than a frontal depression.
Hurricane, typhoon and cyclone are all local names for tropical revolving storms.
We hit a typhoon just to the south of Japan, and I'm not sure whether it was our fault in navigating incorrectly or whether it was the typhoon had actually changed direction, but we went right through the eye of this typhoon, or rather the eye of the typhoon went right over us. That was quite incredible, because as we approached the eye, the storm was obviously blowing, I would say, in excess of force 12. Completely white as far as visibility was concerned, white outside, just spray everywhere. Ship rolling horrifically, pitching horrifically. We passed through this wall of water into the eye, and it was just instantly calm, quite incredible. Flat sea, crystal clear sky, stars shining, and it was quite amazing. We could see this clearly on the radar all around the ship. And I think the worst part of it was we knew we'd have to go through the other side and basically straight back into all that weather again.
The pattern of isobars around the centre of such a storm is almost exactly circular. At the edge of the storm, the winds cross the isobars at about 45 degrees. Around the central eye, the winds are at their most intense and are almost parallel to the steeply curved isobars. We still know relatively little about how TRSs arise, but it is known that, to occur, the sea temperature must be at least 26 degrees Celsius. They usually start on the western sides of the oceans between latitudes 8 and 20 degrees. They peter out several days later at a maximum of around 40 degrees. Tropical storms move quite quickly, and their paths are unpredictable. Generally, they move westerly, veering northwesterly in the northern hemisphere, westerly, then southwesterly in the southern hemisphere. So far, their speed over the ocean would be about 10 to 12 knots. At around 20 degrees latitude, they quite commonly recurve to head northeast or southeast, the point of recurvature being known as the vertex, and may now start to travel at more than 20 knots. But this description is a general one. Some storms continue on their original path, and individual tropical storms can move in a quite erratic fashion. The winds generated by such storms are extremely high, up to hurricane force 12. In the second part of this package, we will describe how to establish the ship's position relative to a tropical storm, and what avoiding action to take. So far, we have considered why regions are hot or cold, experience low or high pressures, and become windy or stay calm. But how can we predict changes in the weather? With so many variables interacting with each other, forecasting the weather for a particular area is always going to be an inexact science. However, in the last 20 years or so, great advances have been achieved.
We've had a lot more data coming in from satellites, from observations from aircraft, from balloons, from all types of equipment that have been available to us. We've also been able to increase the computing power considerably, as I'm sure everyone's aware of, and our understanding of the physics of the atmosphere has improved as well. So all of those combined has given us the capability to produce better forecasts and going out further in time as well.
More and more dominantly, we have satellite data. A single satellite can supply millions of observations of data, an enormous flood of observations. And what's happened over the years is a lot of money has been spent on satellites. The satellites got a lot better. And they're now becoming almost a dominant form of observation. And you just get an incredible flow of data from those.
But the real key to the increasing accuracy of weather forecasting by the major national centres, such as the UK Met Office, has been computer power.
In our basement here, we have a supercomputer, which is a massively parallel machine, whereas like a traditional computer, or the computer you might have on your desk at home, does one thing at a time, but does them very quickly. The computer we have does the things, individual things, far more quickly than your computer at home, and it does many of them simultaneously, all at the same time as each other.
So can we now expect totally reliable forecasts?
Unfortunately, it's impossible to ever guarantee a perfect weather forecast into the future. If we're looking to forecast for, say, a week ahead, what we'll do is have 50 different versions of our initial conditions, all very slightly different from each other, and then we'll solve the equations for each of those, which will give us 50 answers for what the weather's going to be like in a week's time. We don't know which one of those answers is going to be right. They'll all be different, and they'll all be equally likely to be true. But what we can say is we can give a range of solutions in which the reality is likely to lie.
The principal weather bureau provide weather forecasts for the whole planet, land and sea. But in addition, there are commercial firms that can provide a dedicated weather routing service for the marine industry. The software predicts the progress of a vessel on a variety of routes, taking into account the weather expected at each position and the effect that wind, wave and current will have on its speed. The computer uses known performance characteristics for the ship and will work out the optimum route, which in many cases may not be the shortest great circle route. The calculations will be refined in the light of the ship's loading and trim and the headway it makes immediately after departure. This is not simply an exercise in number crunching, however. Such a service is staffed by meteorologists with considerable maritime experience who adjust the computer's predictions in the light of their own knowledge. Adding 10% to the minimum great circle distance can still save time and fuel if it avoids bad weather conditions. So far, the main component of the weather we have examined has been the wind. But it is not normally the wind that has most effect on slowing a ship's passage or causing damage. That is done by waves. Waves are caused by wind blowing over water, and generally the stronger the wind, the higher the waves. Sea waves are those produced by the wind blowing at the time of observation. Swell is the term used for waves produced in the recent past by winds blowing some long distance away. Swell waves typically have a long wavelength and a smooth, oily appearance. The passage of a wave represents the movement of energy. In reality, the water remains in much the same place. If we could attach a label to an individual particle of water at the surface, we would see that as a wave moves past, it undergoes an almost circular motion. The diameter of the circle is equal to the wave height, h.
Below the surface, the water particles have orbits which become smaller and more elliptical, until at a depth equivalent to half the wavelength, L/2, there is practically no motion at all.
In open waters, a wave is nearly symmetrical, with the crest embracing an angle of about 120 degrees. The wave's period, T, is the time for two successive crests or troughs to pass a fixed point. If the wavelength L is measured in meters and T in seconds, then L equals 1.56 T squared. Modern forecasts sent to shipping now incorporate information on wave direction and heights. Of course, most waves are not uniform. A train of waves will usually include waves of different heights, lengths, and period. But we can make two general statements. Sea waves always travel to leeward, and large waves always overtake smaller ones. The Beaufort scale is the well-established method of relating wind speed to the appearance of the sea. It was first put forward by Admiral Beaufort in 1808 and remains a very good and consistent guide as long as it is applied to open waters away from land or tidal effects. All mariners will benefit from knowing the Beaufort scale. The scale goes from 0, representing a calm, mirror-like sea with wind less than 1 knot, up to hurricane force 12, when the air is filled with foam and spray and visibility is very seriously affected. Waves breaking down on a ship's structure can exert huge forces and bending moments on the hull and may cause catastrophic damage. The second part of this training package will show how to minimize the danger presented by waves and will describe a heavy weather avoidance system fitted to some ships. Breaking waves are a particular hazard because the water falling down from the crest might be travelling at twice the rate of the wave. So a 30-knot wave could suddenly present water travelling at 60 knots. If a ship is travelling towards the wave at 20 knots, the relative impact speed could be as high as 80 knots. Given that just 1 cubic metre of water weighs more than a ton, the structural damage can be severe. A wave tends to break with a spilling motion when its height-to-length ratio, h/L, exceeds 1 in 7, and this can happen from Beaufort wind scale 3 upwards. A wave spills when, having got steeper, but remaining relatively symmetrical, the crest becomes unstable and spills down the front face as a surge of foam. At high wind speeds, say from Beaufort 12, both the lengths and heights of the waves will increase significantly, and the breaking motion is called plunging. A plunging breaker occurs when the waveform becomes asymmetrical. The top travels faster than the body of the wave, resulting in it curling over and plunging down the front face. A plunging breaker of height 8 meters, say, would easily capsize a small fishing vessel. In shallower waters, the situation gets worse. As waves approach a coastline, their speed and length decrease, but their heights remain the same or may even increase. This means the waves become steeper. A wave may break when the water depth is half the wavelength. Waves generated by a storm might easily have a length of 400 meters. Thus, on meeting the continental shelf depth of 200 meters, these big waves can start to break. Another reliable formula is that a wave starts to break when its height divided by the water depth equals 0.8. So as it nears the coast, the situation becomes more severe. For each breaking wave, the amount of foam indicates the amount of wave energy suddenly being released. Here we see a bulk carrier which was grounded off the west coast of Norway after its engine failed. Breaking waves caused the ship to split in two. The crew were rescued, but the environmental damage was considerable. The approach to the shoreline can have other effects on the behavior of waves. Refraction, similar to the bending of light waves by a lens, occurs particularly where there are protruding headlands and where waves pass over a shallow bank. This computer simulation shows that 20 kilometers after passing over the shallows, the waves will coalesce at one point. And where you might have expected sheltered waters, they form abnormally steep, dangerous waves. Rogue, or freak waves, are the greatest danger you are ever likely to face. The sudden coming together of different waves at particular moments can produce waves of staggering height, and troughs so low that they have been described as a hole in the ocean. Significant wave height is defined as the average height of the highest one-third of the waves. In deep waters, on average, one wave in 3,000 will be twice the significant wave height, and this is the exact definition of freak wave. One wave in 25,000 will be 2.25 times the significant wave height, and one wave in 300,000 will be 2.5 times the significant wave height. During 1 month at sea, any vessel is likely to meet 300,000 waves, and so is likely to encounter at least one very dangerous wave. This computer simulation illustrates the principle. The waves, all travelling in one direction, are of varying heights and speeds. It takes just one momentary coming together of several waves to produce the freak wave. Mariners should also note when the sea waves and the swell are from different directions. The vessel might be pitching or rolling more than expected. This again is a situation in which a freak wave might be encountered. Freak waves are also more likely to be encountered where the predominant direction of the waves is counter to the prevailing current. For instance, the Agulhas current off the coast of South Africa. In theory, freak waves can happen anywhere, but these are the areas most noted for their occurrence. The highest officially recorded wave was 34 meters. Apart from wind and waves, there are two other weather hazards seafarers have to face: fog and ice. Fog is suspended water droplets hanging in the air, really the same as cloud, but at surface level. The strict definition states that fog reduces horizontal visibility to 1,000 meters or less. If visibility is from 1,000 to 2,000 meters, the terms mist or haze are used. Fog is caused by the cooling of a large volume of air below its dew point, and the method by which it is cooled determines the type of fog. The most common type is advection or sea fog. This occurs when relatively warm air passes over a cooler sea surface. There are certain areas where this condition is more common. Off the Grand Banks of Newfoundland, where the cold Labrador current meets the warm air associated with the Gulf Stream. Off the southern coast of Japan, where the warm Kuroshio meets the cold Oyashio. And in the English Channel in the spring, when warm southwesterly air meets the colder waters coming from the North Sea. In the second part, we will detail observations you can make to predict the likelihood of meeting advection fog. Frontal fog arises when air masses of distinctly different condition meet, such that cold air cools relatively warm and moist air. Thus, the usual location of frontal fog is at a warm front, or warm occlusion, in temperate or high latitudes. Radiation fog only forms over land, but if conditions are right, it spills out onto the sea to a distance of 15 kilometres or so. It occurs when, on a cold, clear night, the land loses heat rapidly through radiation, and the air close to the surface is cooled below its dew point. Because the cold air is heavy, the fog will drain down into valleys and out over the sea. It will usually disperse after sunrise as the land warms up again. Finally, Arctic sea smoke. This occurs when the air is cold and dry, about 9 degrees Celsius cooler than the sea surface temperature. Rapid evaporation takes place from the sea surface and condensation occurs, giving the appearance of smoke rising up to 15 metres above the sea and hiding many ships except for their masts. The remaining weather hazard is ice. Not only the ice which floats, mainly submerged in the sea, but the ice which forms on ships' superstructures and can have a significant effect on weight distribution and stability. This ice is formed either from freezing rain or from wind-blown spray. There is an increased chance of capsize in heavy seas if the vessel's decks are weighed down by ice. Essential equipment, like radio antennae and lifeboat equipment, will be badly affected. Ice which floats in the sea is either sea ice, which has formed due to the sea becoming sufficiently low in temperature, or icebergs, which have broken off the end of glaciers, or the Antarctic ice shelf. In both hemispheres, icebergs are likely to move much further into the temperate latitudes than sea ice, and much later into the spring. For instance, the peak season for icebergs off Newfoundland is March to July. Sea ice forms slowly, firstly in shallower waters. Once this ice has fully developed, it is known as field ice or pack ice. It might be several centimetres or several metres thick, and individual pieces 20 metres across are known as floes. Pack ice will be termed very open, open, close, or very close, depending on the distance between the floes. In the second part, we will outline some of the signs which warn of pack ice. Icebergs present a greater danger, as they are isolated masses of ice, mostly submerged and so invisible, floating in an otherwise open sea. Antarctic icebergs in particular can be several kilometres across. Bergy bits is the term used for icebergs showing 1 to 5 metres above the surface, and growlers, those with up to a metre showing. They are particularly dangerous, as often they are obscured by waves washing over them and have the potential to scrape along the bottom of the ship and damage the propeller. These smaller bergs are unlikely to be detected by radar, especially in severe weather. Good information on the whereabouts of ice is available from polar orbiting satellites and from the ice reporting services provided by the United States and Canada. Ice, fog, and the other weather conditions we have considered are probably the biggest single factor in determining whether voyages remain safe and on schedule. So, is the world's weather changing in any significant way?
The evidence for global warming is in my view, pretty well overwhelming. One of the things that's happened is we've gone back into the past, we've looked at how the Earth is warming up, and we compare that with how our models of the atmosphere shows the Earth ought to be warming up due to greenhouse gases. And there's a very high match between the two.
This terminology, global warming, is a mixed blessing, and it does give the wrong impression at times, because within the changes that we may get some places becoming windier, other places the wind's becoming lighter, some places becoming wetter, drier, etc., and other places becoming significantly colder due to global warming in that terminology.
One possible example are hurricanes. Some years there are more hurricanes than others, but hurricanes depend crucially on the temperature of the sea surface. If the sea surface is too cool, then hurricanes can't form. So it naturally follows that if the sea surface is warmer, as it will be ultimately for global warming, that hurricanes can form over a larger area. And also if the sea surface is warmer, there's going to be more energy available from the sea surface. So there's a clear possibility that you might get more intense hurricanes in the future. But what I should say is that what we're talking about here are possibilities, not forecasts.
For the present, a constant monitoring of the weather and the correct interpretation of weather forecasts will provide real benefit in ensuring a safe and economical voyage. The importance of on-board weather observation and the hazards associated with different types of sea condition are dealt with in part 2 of this package.